To finish our review, we're going to look at antiderivatives, specifically indefinite and definite antiderivatives, or integrals. So first, let's look at the indefinite integral. This is defined to be the set of all antiderivatives of a function, where an antiderivative of a function f of x is a function whose derivative is that function. In short, to find an antiderivative, we're going to go backwards through the derivative process. Sometimes this is an easy thing to do, and sometimes we're going to see it's a very difficult thing to do. Let's look at some notation we're going to use a lot of. Here, the integral symbol, this long S-looking thing, with a dx on the outside means find all antiderivatives of, and then the dx tells us with respect to x. So this dx is some instructions that tell us something about the function we're going to find. It's going to be with respect to x. But again, this is instructions similar as the ddx was instructions. Also, we're going to have this plus c at the end of our integrals. And f of x plus c is going to be the set of all functions of the form f of x plus a constant. It's just a shorthand to be able to say, in fact, we could say that f of x plus c is actually going to be the set of all functions f of x plus a constant c such that c is a real number. This is a set notation, but this is going to be a family, an infinite family of functions. It represents an infinite amount of functions. So let's look at this indefinite integral. Let's find the integral of 2x to the fourth dx. And note that this is a sentence that reads, find all antiderivatives. Let's actually write this out. Find all antiderivatives of 2x to the fourth with respect to x. So we're trying to find all functions that have a derivative of 2x to the fourth. So without doing some actual rules here, let's just try to play around with what will have a derivative of x to the fourth. Maybe we can think of something like x to the fifth will have a derivative of x to the fourth because the derivative of x to the fifth is 5x to the fourth. But we need to take care of that 5, and we can do that by saying, this is an idea, we should say. But to take care of that 5, I can write a 1/5 x to the fifth. And then I need to take care of the 2, which I can do by a 2/5 x to the fifth. We'll talk about how I did that in just a little bit here. But 2/5 x to the fifth is one antiderivative. And I can verify that by taking the derivative of 2/5 x to the fifth would be 2/5 times 5x to the fourth. 5's cancel out, and we're left with 2x to the fourth. But what I need to find is a set of all antiderivatives. So one way I can do that is I can say this is going to be, the indefinite integral is going to be 2/5 x to the fifth, our one antiderivative. And if I add a constant to that function, that gives me any other antiderivative. Because the derivative of a constant is 0, it's not going to make any difference. So when we have indefinite integrals, we're going to add this plus c because we're looking for all antiderivatives of that function. So let's look at some basic rules for antiderivatives. Sometimes there's some nice easy rules, sometimes there's more complicated things. In fact, our first 2 sections of this course are going to look at 2 antiderivative techniques we're going to look at, which are more complicated than what we're going to look at here. So first big one is the reverse power rule, something I just kind of used in that previous page. The integral of x to the n dx is going to be 1 over n plus 1 x to the n plus 1. This is the opposite of bringing the power down out in front and decreasing the power by 1. Now we're going to increase the power by 1, and we're going to have to divide by that new power to get rid of that, bringing the power down out in front. And note this is true for all n except for n equals -1. We have that the integral of 1 over, I should say not 1 over n, but 1 over x to the first is going to be something different, natural log of absolute value of x plus c, but we'll see that on the next page. Okay, so a reverse power rule, note we have the plus c here because it's an indefinite integral. If I have, and also maybe we should say that we can verify this by just taking the derivative of these antiderivatives. This will give us the n plus 1, bring it out in front, decrease the power by 1, and then the derivative of a constant is 0. That will give us just x to the n. The derivative of a constant, we're just going to slap an x onto it, plus c. If I add or subtract two functions together inside of an integral, I can take care of those integrals separately, just like we did for derivatives. And same for constants, I can bring them out in front. Some other rules we have, the antiderivative of e to the x is just e to the x. Same thing with since the derivative is itself, the antiderivative is itself. And then we're going to say that if I have e to the kx for some constant k, we can kind of do this backwards chain rule sort of thing. And instead of multiplying by the derivative of the outside, I can divide by the derivative of the inside. 1 over k e to the kx plus c. And you can verify that by just taking that derivative very quickly. The antiderivative of sine is going to be negative cosine. That's because the derivative of cosine is negative sine, so the negatives are going to cancel each other out. And same thing when I have the integral of sine of kx, I can have a factor of 1 over k to get rid of that k constant from the chain rule. The antiderivative of cosine is positive sine, and same kind of thing with the k factor there. And then the rule we talked about, the integral of 1 over x is going to be natural log of absolute value of x plus c. And again, the absolute value bars here are important. Note that when we're talking about in Wiley Plus, the online homework system, you need to write down natural log of parentheses absolute value of x. It's one of the finicky things that Wiley Plus does, and I will send an email out about that as well. The other kind of integral we're going to look at is a definite integral. We define the definite integral as the area under the curve of a function, or more specifically, the signed area from the function to the x-axis. So very quickly, think about some function here. The area above the x-axis is positive area, and the area below the x-axis is negative area. If you add everything together, it gives us the area under the curve. And we can evaluate definite integrals by finding the area, or we're given the fundamental theorem of calculus, which we're going to abbreviate FTC, which gives us a way by finding this area by finding an antiderivative. And this is our link between the area under a curve and antiderivatives, and why we call both of these things integrals is because we use the antiderivatives in both. So the fundamental theorem of calculus says that if you have a continuous function, and we're going to say that f of x is an antiderivative of f prime, that's because if you take the derivative of f, you get f prime. Then the definite integral, which is the integral from bounds a to b, that's saying the first bound is a, the second bound is b, that's where the area is going to be taken, of f prime is going to be f of the top bound minus f of the small bound. So we're going to find the antiderivative and plug in the bounds. So let's do an example of that. Let's find the integral from 1 to 3 of 3 over x squared dx. So first thing we need to do is find an antiderivative of 3 over x squared. And it might help to write this out as 3x to the negative 2. The antiderivative here is going to be 3 over negative 2. And then we're going to, sorry, that's not true. 3 over negative 1, x to the negative first power. We're going to add 1 to the exponent, divide by that exponent, and we're going to evaluate from 1 to 3. So this notation means evaluate from x equals 1 to x equals 3, which is going to mean we do this f of 3 minus f of 1 business. So overall we have, this is going to be negative 3, 3 to the negative 1, minus negative 3, 1 to the negative 1. Rewriting this, this is going to be negative 3 over 3 plus 3 over 1, negative 1 plus 3, which is 2. And this is an area that we're finding. This is like 2 units squared that we have. So when we're doing these definite integrals, it's important to find the antiderivative first. All we need is one antiderivative, not all of them. And then we're going to evaluate the top bound minus the bottom bound using the fundamental theorem of calculus. And our answer is a number, not a family of functions. That's a big difference between the definite integral and the indefinite integral. Last thing we're going to do in this section is we're going to look at improper integrals. If you took Math 131, you should have already seen improper integrals. If you took Math 141, you may not have seen improper integrals, as it's more of a Calc 2 subject. But we're going to quickly go over some of the basics of these. And we're going to use these pretty soon here in a couple weeks when we think about probability. So there's two kinds of integrals we're going to look at. It's called improper because the bounds are going to include infinity. There's other kinds of improper integrals, but this is what we're going to focus on. You could either have one of the bounds be infinite, so something like a number to infinity, or it could be both bounds infinite. And what this represents is if you have some function here, some value a, you are finding the area under the curve from a to infinity. It's an infinite area that we are finding. Or in the other case, we have maybe our function looks like this. Negative infinity to infinity is going to be the area under the curve total from negative infinity to infinity. And what's interesting about these is that the area, even though it's an infinite area we're looking at, it actually comes to be a finite number in a lot of cases. And if we say that it actually does equal a finite number, if the area equals a finite number, say if the integral, that is the area, is a finite number, then it says it's going to converge. If not, we're going to say it's going to diverge. And we'll look at some examples of both convergent and divergent integrals to see what we're talking about here. So, first kind of thing, we're going to try to decide if 1 over x squared from 1 to infinity converges or diverges. We think about the graph of this function. 1 over x squared is going to get smaller and smaller and smaller. And the question really comes out to be is, as x gets bigger, the area is getting smaller and smaller. Is it getting smaller fast enough that it's going to converge? So in this example, we're just going to show what we're kind of talking about here. We're just going to go through the process of finding this. We're going to say this improper integral, we're going to rewrite as one to b, and b here is going to be a very big number. We're going to let b get bigger and bigger. So b is a big finite number. So instead of thinking about an improper integral, we're going to make this a proper integral, 1 to b, so 1 to a million, 1 to a billion, 1 to something bigger than that. And then we're going to let b get bigger and bigger and see what happens to the integral. In the next video, we'll see some other ways of thinking about dealing with this improper integral. But in this case, we're going to think about the limit. We're going to take care of this integral. So this integral, the antiderivative of 1 over x squared is going to be negative 1 over x. We're going to evaluate from 1 to b. Evaluating means that I'm going to write this as negative 1 over b minus 1 over 1. Sorry, minus negative 1 over 1. Again, that's going to be negative 1 over b plus 1. And if I take this limit, if b gets really, really big, this 1 over b is going to go to 0, which means this whole limit is equal to 1. And this is the area under the curve. And since it's a finite number, we say that the integral converges to 1. In the next video, we're going to look at another example or two of kind of diving into the details of this improper integral a little bit more.